Hello everyone, welcome to the 8th talk this Michaelmas term. My name is Gia and I'm the President. We're joined today by members of the committee, Rob, Yikwon and Alda at the door. Welcome, and we're delighted to introduce you to our speaker this week, Professor Peter Norreys, for his talk on the prospects for high-gain inertial fusion. Thank you.
Thank you very much for the invitation to address you, and I really appreciate it, and I'm delighted to receive it. And you can see here that I've got quite a colourful display of the Archer National Supercomputer, so I always try and put on a tie which actually matches the colours in the diagram. But I've got the rainbow flag as well, which nicely matches that one. So I used to have my office, it was there, and on that window in the Townsend building, but I was moved out in the summer, and I'm now on the 3rd floor of the Lindemann building. So if you need to come and see me, just you know where I am. So I wanted to first of all acknowledge all the different collaborators and funding agencies who've supported my research over the years. The Central Laser Facility, the EPSRC, there's Alder Masterman, and then there's John Adams Institute, Ludwig Maximilian University in Munich, and Shanghai Tech University in China, and Living Optics, which is a spin-out company which my former students and I started in 2020, and we're just going through the second fundraising round now, and we should be raising about £48 million in total over those 5 years. So another spin-out company, which is really nice, and they're funding some of our research. So what I wanted to do is to give you a brief introduction to inertial fusion, just what it is, why it is interesting, why we want to do it. And then I want to talk to you about the development of a new multi-scale simulation toolkit for inertial fusion, the future work, and the work we're actually doing at the moment with our group in the Clarendon laboratory. In particular, it's laser plasma instabilities, radiation hydrodynamic fuel assembly, thermodynamics for equation of state, and fully kinetic modeling of burning plasmas. We've got early results, they're all very promising, and I wanted to share the excitement of the students who are actually doing this research, and in particular, optimizing fuel assembly for fast ignition, and then doing integrated tests for dual hemisphere designs, which I'll talk to you about, and then extending it to other high density physics research applications. So it's not an individual application, of course, myself. This is my research group, and you can see that this is Dr. Rami Abu-Shobeya, Dr. Robin Timiz, and then we have the graduate students, who are Edward Atonga, Robin Wang, Sunny Howard, Elliot Dennis, Lily Zhang, Jordan Lee, Abigail James, Heath Martin, Rusko Ruskov, and our new student who's just joined, and I haven't yet taken his photograph properly in a relaxed manner, Joshua Redfern. I would say that we've got quite a big group, but 4 of them are going to graduate this year, so it's all going to suddenly shrink again in the normal way of academic life. So the inertial fusion research, we're right at the forefront of this topic, and you can see here we're publishing in the Physical Review, in the Plasma Physics Control Journal of Plasma Physics, Plasma Physics Control Fusion, and Physics of Plasmas. The other half of my research group is doing extreme field science. In particular, Edward Atanga is looking at the generation of gravity waves using high power lasers. I won't be able to talk to you today about that topic, but certainly after the talk we'll be able to tell you a little bit about it. Lily Zhang is looking at the collision of 3 petawatt lasers and then generating a 4th laser beam coming out from the quantum vacuum. That was written up for Communication Physics, published in June this year, and provided quite a lot of excitement in the national press and international press, which you may have seen. Robin Timiz has been looking at the second nanocoulomb pulse electron bunch generation via an absorption mechanism for petawatt laser plasma interactions. And then Sunny has been looking at single-shot spatial temporal measurements using petawatt laser pulses. He's been doing this work in collaboration with the LMU facility in the Kalle facility in Garching, Germany. So we have a couple of nice articles in Nature Photonics and Optics Express. It just shows you that there's quite a lot of broad range of topics which we're interested in. The applications of high-power lasers and petawatt laser plasma interactions are quite vast, and so you can see that we've got this topic called Raman amplification. The idea really is that you have a pump beam coming in from this side, and then a seed beam which is reduced in wavelength, so that the laser beam generates this stimulated Raman scattering, which is a stimulated electromagnetic wave and a plasma wave, and then the energy is transferred from a seed beam from the pump beam going in this direction to a seed beam in the opposite direction, and then you can generate very, very large pulses of energetic pulses. This is the region towards the X-watt lasers in the next decade or so. Then you've got, of course, the plasma Wakefield accelerators. So you have a really intense, really short laser beam, comes in, expels all the electrons, which you see here, and then there's a positive charge left, so the electrons are then slowed down, and then you get this structure, longitudinal structure being generated, and then the electrons which are in the accelerating area of the field then get accelerated to mega electron volt energies. In fact, the world record at the moment is about 8 GeV being generated by these laser Wakefield accelerators. Then you've got these parametric instabilities, which are basically how you actually take energy from one really intense laser beam and put it into another one, which can be deleterious for inertial Raman fusion for direct drive, but for indirect drive is actually one of the ways that the National Ignition Facility has actually achieved ignition. And hyperspectral imaging, as I say, that was the topic which actually was the basis of the company Living Optics, which we set up and spun out, and it allows you to do really ultra-fast imaging of phenomena, which is really exciting, and we're talking about getting femtosecond frames, maybe 10 femtosecond, two-dimensional frames at different colours, which is really quite an extraordinary result. Robin Timmis is at the moment, along with Elliot Dennis and Joshua Redfern, down at the Rutherford Afton Laboratory at the moment. And as you remember, that in 2023 there was Nobel Prize in Physics was won for attosecond duration physics. And one of the ways they did it was to generate harmonics of the laser frequency and in a gas target. And they were using the harmonics as a way of interrogating other matter. And what you see here is that we're doing an experiment at the Rutherford Lab at the moment where we've got orders and orders of magnitude brighter intensity on those X-ray, on those harmonics being generated using a laser solid interaction. So this has huge implications for attosecond science in the future, and also, of course, for inertial fusion energy research. So that is one of the reasons they're not here at the moment, and we've been quite busy interacting with them. The experiment finishes on the 19th of December, which is quite close to Christmas, of course. But the exciting results coming out from that experiment as we're talking. So why fusion energy? Obviously, we have abundant, effectively limitless fuel supply. We have energy security. It's locally sourced. We don't have to rely upon Russia or other foreign agents who are actually cutting off the gas supplies, as they did a few years ago in Germany. We have low environmental impact with low greenhouse gas emissions. We have a very high generating capacity at an optimum level per plant. It's compatible with existing electricity infrastructure. The local plant location and transmission lines are there, and as we're going towards small nuclear reactors, then it's equally compatible with those. It's inherently safe. It's so difficult to get fusion working that if anything goes wrong, it just stops. so it's inherently safe. And power, of course, whenever we need it. And it's not just, of course, a power supply, which you can imagine, but also in vast areas of the world, there is a great shortage of water. And so you can imagine that a high-temperature plant can provide options for hydrogen production and for water desalination, which is another great achievement, a goal, I think, which we can work towards. I would also say that towards the end of the century, I should imagine that we would want to suck out quite a lot of the carbon dioxide out of the atmosphere. And of course, to do that, you would need quite a lot of energy to do so. So if each nation devoted a portion of its fusion energy plants to actually extracting carbon dioxide from the atmosphere, it could actually go some way to removing that particular greenhouse gas from the atmosphere. We have a fusion reactor. It's called the Sun. It's about 93 million miles away from Earth, and of course, it's absolutely gigantic. The Sun actually contains 99% of the mass of the solar system. So absolutely vast, as you can see here, just to give you an indication of the scale of the Earth compared with the surface of just a small sliver of the surface of the Sun. And because it's so huge, its gravity is vast. So then we have to say what stops the Sun from collapsing under gravity. It was a big question, actually, when you look back on Lord Kelvin in the 19th century. He calculated that if you didn't have a fusion reaction in the centre of the Sun, it would actually collapse after about 30 million years. So he was debating with all the people in the paleontology people, who just discovered all the fossils from, the giant dinosaurs and so on, how old the Earth was, or how old the solar system was. But anyway, we did find out that it was actually due to fusion. And you can see here that in the center of the core of the Sun, we have the high density region. This temperature is 15 million degrees centigrade. The density in the core of the Sun is about 150 grams per cubic centimeter. And it takes an enormous length of time for radiation, which was generated in the core of the Sun, to emerge and escape eventually to the photosphere, which you can see here, which is what we obviously observe and use as our energy source. So the actual Sun itself has got a radiative zone and convection zone, and so on. But very interesting topic on stellar structure and evolution. So the fusion fuel for the Sun, of course, is hydrogen. So two protons colliding with each other. Cross-section is quite small, but there's such a vast number of hydrogen atoms in the Sun that it actually allows you to propagate the fusion fuel and actually producing this pressure which actually balances the gravitational force inwards. When we're talking about a terrestrial fusion plant, you've got deuterium and tritium, which produces helium and neutrons. So the deuterium has got one neutron, one proton. The tritium has got two neutrons and one proton. And then when they form, you basically produce a helium atom and a neutron. So this helium atom has got, it's called an alpha particle, and it's got 3.5 megaelectron volts in energy. And the neutron has got 14.1 megaelectron volts. So over 17 megaelectron volts being generated in each of these fusion reactions. And it's about 1 million times or greater than the chemical reactions that you can imagine, which would normally be undertaken. And just to give you an indication, if we have a tanker from Saudi Arabia or whatever, you can see this vast amount of energy in these super tankers, and then you've essentially about 70 milligrams, or 70 grams, sorry, of deuterium tritium equivalent to that entire container of oil. So it's a vast. It just gives you an indication of the scale of the energy release from a fusion reaction. So how do we make fusion energy work? We need to heat it to very high temperatures. 100 million degrees centigrade is normal. It's about 6 times hotter than the core of the sun. The core of the sun is about 15 million degrees centigrade, but we need to be 6 times greater than that. So, of course, no vessel can withstand direct contact with those sorts of temperatures, and so we have to confine the matter. And we can do this in 2 ways. We can do it by containing the matter at low density over long time scales using very large magnetic fields, or we can have a very high density over a very short time scale using intense lasers. So essentially what is we have to exceed what's known as the Lawson criteria, which is the density by the confinement time by the temperature being above a certain level. And so if you have low density but high, but over a long time, you can exceed the Lawson criteria at the same time as it's equivalent to having a very high density over a very short time. So how bright are these lasers? This is a picture which I saw from the internet. And a typical laser, which I've got here in my hand, a laser pointer. It's also green. It's an infrared frequency tripled to green using crystals, wavelength around 520 nanometers, limited usually to about 5 milliwatts. Any higher can cause eye damage. I would say it's used to torment cats, and I'll show you an example of that in a moment. But we have many universities and industries use more powerful lasers than those. And you can see here as an illustration. I can see you, let you show it again. Perfect. Anyway, I think really what we can think about, whether it's magnetic confinement fusion or inertial confinement fusion, you can think of it as equivalent to the jet engine. So essentially, with the magnetic confinement fusion, you're putting in the fuel into this confined plasma, confined by the magnetic fields, and is essentially what you would do with the jet engine, where you're continuously importing fuel into the jet engine. And internal combustion engine is rather similar to what we do with the inertial confinement fusion system. You compress the material to high density, spark it, then it explodes, and then you put in more fuel, compress it, spark it, explodes, and so on. So it's kind of like an internal combustion engine. And I put this Ferrari up because this is rather a beautiful colour, and I think we all aspire to be driving these things, so why not? The Cullum Centre for Fusion Energy is down the road. It's about 8 miles south of Oxford in Abingdon, and it used to be home to the Joint European Tours. It just closed this last year, but it's basically a device where you're actually confining the plasma in these using these magnetic fields, and it's a very large machine, a very huge number of. It was a beautiful thing to go and visit, and of course the ITER facility in the south of France is the next machine to become online on this kind of device. So there's the Cullum Centre for Fusion Energy. As I say, it's a vast laboratory, employs thousands of people, and they're working about 8 miles, and it's just east of Abingdon. There's also the Rutherford-Ampton Laboratory, which is also down the road. It's about 15 miles south on the A34 as you're going down towards Newbury and to the south coast. And this area circled here is the ISIS neutron spallation source. So this is a cyclotron accelerator, produces protons up to 800 MeV, which are then collide into a high Z target and produce a large number of spallation neutrons, which are then cooled in a moderator. And those neutrons are used for X-ray neutron diffraction for all sorts of different topics, biochemistry, engineering, and so on. So this is a brilliant national facility. And here is the diamond light source. If you're coming up from Oxford from the south coast, you see the building on the far left as you're going on the A34. You think actually it's a football stadium, but in fact it's actually the cyclotron diamond light source. Again, it produces electron beams up to 3 GeV in this case, and each one of them, as they're bending past the circle, emit synchrotron radiation and about 30 odd light station sources. Again, doing all sorts of X-ray diffraction experiments for all the different light sources and so on. And here is the central laser facility, which is in the ringed here at the end of the main building of the Rutherford Apton Lab, called R1. And at the moment the Vulcan laser facility is being upgraded. It's been closed recently, and the walls are being taken apart and it's being reconstituted, again for fusion energy research for academics across the nation. So here are the capacitor banks. Then you have some glass laser amplifiers going up to what's known as a petawatt peak power and into a petawatt target area. And here is what's known as a long pulse target area east and target area west, which were combining the long pulse beams and short pulse beams for all sorts of laser plasma interaction studies. About 35 miles south of Oxford is just south of Reading is Aldermaston, and they have constructed Orion, which is a laser facility studying behavior of matter under extreme conditions of density and temperature. So they combines 10 laser beams operating over 1 nanosecond, and 2 of these laser beams are at petawatt peak power, and they operate at about 1 picosecond. And the interesting thing about the Orion laser facility is that 15% of the facility is open to academics interested in fusion energy research, which is rather splendid. So here are the long pulse beams on Orion. They're quite, this machine cost about £200 million to construct. It's now undergoing its mid-term refresh, and will be back up in operation towards the end of next year. So here are the short pulse beams for the petawatt facility. And this is built in complement to the machine which is built at the Lawrence Livermore National Laboratory, which is called the National Ignition Facility. This is a $4 billion laser facility. It's got 196 beams, produces 2 megajoules of laser energy at third harmonic, which then is directed into the target chamber. Just to give you an idea of the scale of this machine, this is the guys who are looking after the long pulse arm of the National Ignition Facility. The target chamber itself is pretty huge. It's about at least 10 meters in diameter, so you can see that actually getting around in that instrument is quite fantastic. And here is the laser beams coming in from the laser bay, which I showed you, and then the frequency conversion is happening at the entrance of the target chamber. So there's beams coming in all the way around the top of the chamber and then at the bottom, and then the diagnostic ports are usually around the center. Again, you can see the size of the machine by the scientist at the entrance hole. It was used as a prop actually for Star Trek. I think it's Into Darkness, I think so, when Captain Kirk passed away from neutron radiation. So there you are. The machine is 500 terawatts in total, so compared with our laser pointer, which I showed you earlier, is pretty large, so fabulously bright. So what is the principle of inertial volume fusion? In essence, it's the ideal gas law. You have the pressure times the volume is constant times the temperature. So if you go, the volume goes down, obviously the pressure and the temperature go up. And that means that if you have a beryllium shell, and then you have deuterium fuel frozen on the inside of this on this shell, then as it's compressing, then it'll produce those conditions for fusion. Obviously, that's rather a simple way of looking at it, but it's basically the essence of it. And this is the size at which you're trying to compress it. Now, I don't know how many of you have got your balloons when you blow them up at the Christmas time, or your birthday parties, but you're actually trying to compress something down to that sort of diameter. Requires an enormously uniform pressure on the outside of this capsule, and this has been one of the bugbears or the difficulties of actually achieving fusion ignition in the laboratory. Actually getting the uniformity of the irradiation absolutely perfect so that you can actually compress it down to that sort of size. Basically what happens is that as you know from a rocket, you've got the exhaust gases from the rocket, and they essentially impart momentum to the payload, so that it allows you to escape the Earth gravitational field. In the same way, either the direct laser radiation or the X-rays produce this blow-off plasma of very high temperature and into the vacuum, and then the remaining shell starts to implode at very, very high velocities. So that is the rocket effect, which actually is at the core of the compression. So this is an idea that you have this laser beams coming in on the surface of the target at 10 to the 14 watts per square centimeter. The electric field of the laser pulse, it's electromagnetic wave, of course, so the electric field amplitude is more than 1 billion volts per centimeter. So within one or two oscillations of the laser electric field, you're going to have a very hot, dense plasma being formed almost instantaneously. And at 10 to the 14 watts per square centimeter, the temperature which actually is produced is actually something like 100 million degrees centigrade. And then, of course, because you're actually generating it at really quite close to solid density pressure, the solid density, or some fraction of it, the pressure which you can generate here is in the millions of atmospheres of pressure. So this really extreme conditions which you're generating, and then of course the material starts to collapse inwards, and then under these conditions here for fast ignition you have a petawatt laser pulse which comes in and heats the material on a time scale so short that it doesn't have time to react hydrodynamically. So it just gets hotter and hotter and hotter until you get the ignition burn wave starting. So that's the compression of the fuel using a petawatt laser beam. And I did some experiments with my friends in Japan. I led the UK team we published that in Nature in 2020 and 2021, where we demonstrated that this is a potential viable route to fusion energy production. So on the National Ignition Facility, they have what's known as a whole ram target. So instead of directly illuminating the surface of the pellet, you're actually illuminating the inside of this gold can. And what you've got here is shielding, because the third harmonic has been generated, but then the second and the fundamental lights are still propagating into the target chamber. And so these are the second and harmonic and fundamental light shields for the protecting of the other instruments around the chamber. So what's happening is that the laser beams come in, they're hitting the side of the capsule, Then they're producing this very hot, dense plasmas, the same way as you would on the surface of the plasma. But then, of course, it generates a very high Planckian distribution. That then re-radiates and fills the entire element of this hologram target and produces a radiation temperature of around 300 electron volts. I always think of this something like a chicken being put into your oven for, usually at Christmas time, a turkey would take a couple of hours to cook because this enormous amount of energy is being delivered to the chamber. This happens in about 10 nanoseconds. But it's the same principle. You're basically producing a Planckian black body radiation. And the X-rays which are generated then penetrate into the surface of this fuel capsule, and then it starts the implosion. So I always think that what we've got here is we've got a capsule which is at solid density. It's also got this cryogenic temperatures, cryogenically frozen DT ice layer, and of course you're boiling it or producing it from the vapor state into the plasma state very, very rapidly. So in other words, you've got to know the solid state, the liquid state, the plasma state, and you've got to know all of them to be able to understand and to produce the conditions required for inertial ion fusion. So it's rather splendid, as you've actually got to know all of physics in order to get this thing to work. So the National Innovation Facility demonstrated the learning plasma regime in January of 2022, and this is a fantastic achievement. And not long after having entered the burning plasma regime, they actually generated more energy out than was put into the plasma by the laser beams, which is actually the demonstration of the Lawson criteria, and that's the first time it's been ever demonstrated in the laboratory. And inertial ion fusion was published or declassified in 1972. Magnetic confinement fusion was declassified in 1958. And so there's something like a 15-year gap between the effort that's gone into magnetic confinement fusion versus inertial confinement fusion, and the inertial confinement fusion has demonstrated the Lawson criteria for the first time. This is just to illustrate. This is a recent paper. This is published in November the 5th, so only a month ago. And you can see here this is all the different magnetic confinement fusion devices, which you see here. And here we've got the Omega laser facility at the University of Rochester, which is a direct drive machine, which is doing the compression with the directly illuminated capsules. And here is the National Ignition facility with the indirect drive approach. So they've actually surpassed the Lawson criteria, which is fantastic. And the US Department of Energy, Secretary of Energy for the United States government, when this was announced in December of 2022, remarked that it was probably the biggest scientific breakthrough of the 21st century. And I certainly endorse her assessment. Just before the pandemic, in March 2020, I called a meeting at the Royal Society in London, and we had a discussion of all the national laboratory leaders from the United States and from other countries, in the United Kingdom, of course, and elsewhere. And I produced two special issues of the Philosophical Transactions of the Royal Society in 2020 and 2021. And I contributed to this inertial fusion energy report, which is commissioned by the Department of Energy in the Office of Science. And that shows you that everyone is getting prepared for the next steps in the development of fusion energy. So this is a published report in October of this year, Fusion Science and Technology Roadmap from the United States, and they are very gung-ho, if you like, and they're very ambitious in their their approach to inertial fusion energy, and they are really on the decadal timescale for actually building a machine which will actually produce more energy out for the national grid. I'm not sure they'll actually get there in 2035, but it's good that they're actually pushing this forward, and they're also, of course, doing the transition from the public sector research to the private sector, and I think there's something like $9 billion has been invested in fusion energy startup companies in the last few years, so that's not so bad. Burning plasmas, they provide access to this is some articles from the special issue of the Philosophical Transactions of the Royal Society. The burning plasmas, they provide access to new physics, the study of photoionized plasmas, double Compton scattering, Bright-Wheeler processes, and extreme field quantum electrodynamics. The National Nuclear Deterrent, the Lawrence Livermore National Laboratory, is a weapons laboratory. It is for nuclear stockpile stewardship of America's nuclear stockpile. And of course, Aldermaston, where we've seen that the Orion Laser Facility is located, also undertakes research for the UK National Deterrent. And what they are saying here is that they are, because there's a moratorium on underground testing, has been in place since 1990 or so, it basically showing you that current research in inertial fine fusion is able to certify the deterrence decades to come, and therefore they're working closely with the international community to develop ICF science. Another beautiful paper from this article, from this special collection, is George Tynan and his postdoc, and he basically, in his article, he's saying that you've got to be able to compete with renewable sources. The fusion energy is not easy, and nobody should pretend that it's going to be tomorrow. But in 2050, you should be able to see something about, well, maybe the first power plants will be coming online. You've got to be able to compete with renewable sources, so solar, wind, geothermal sources. If your electricity from your fusion power plant is 10 times more expensive than the solar or wood thermal or geothermal or whatever, nobody's going to buy it. So you've got to be able to make sure that you compete with those sources. And you have to, in order to do that, you've got to have a suitable unit size, which George was suggesting was the order of 100 megawatts of electricity. And the third thing is to demonstrate safe and reliable operations. The last thing a fusion community needs is to have an accident like 3 Mile Island or Chernobyl or Fukushima, which actually then turns the public against the fusion power production. So those are 3 criteria which I think are really important. So then there's ways to actually reduce the drive energy. One of them is with this direct laser drive, is to use a zoom focus. Essentially, when you have a laser beam which is about 40 centimeters diameter, it'll focus to a focal spot. But if you shape the laser pulse as it progresses during those 10 nanoseconds, you can actually reduce this focal spot as the implosion is actually happening. This is called zoom focusing. It requires a revolution in optics to actually achieve it, but the guys at the University of Rochester, the second most brilliant optics laboratory in the United States, and that's really what they're planning to do. And then there's the direct drive with argon fluoride with Stephen Obenchain and the Naval Research Laboratory in Washington, DC. And essentially what they're suggesting is that the National Ignition Facility is at third harmonic, which is 351 nanometers. If you reduce the wavelength of the laser light to 193 nanometers, then the ablation pressure can increase, and that means that you can reduce the drive energy requirement quite substantially. Now we're in a physics society, so I'm going to put up an equation. And forgive me if I'm hopefully not going to lose you too much. But essentially, the ignition threshold factor is essentially where you're starting off with a gain, and then it's suddenly increasing quite exponentially, and then it flattens off. And so this ignition threshold factor, you can see here that what's important is the implosion velocity is something like the eighth power of the velocity. So the ignition threshold factor is something like the eighth power of the implosion velocity. This alpha particle is the parametric instabilities which preheat the fuel. So if you want to get a really good implosion, then this has got to be minimized, and so on. The convergence ratio is really significant because you want to maximize it to increase the ignition threshold factor. So it's the eighth power, which is the 12th power of the convergence ratio. Unfortunately, if you go too high in implosion velocity, your shell becomes too thin, and then it becomes susceptible to hydrodynamic instabilities, and then the shell breaks up before you can compress it to high density. So this was an experiment which were done on the National Ignition Facility in 2016 and published in Physical Review Letters by Rick Olson and colleagues. And here's suggesting that actually, here's your convergence ratio on the bottom here. And you can see that as you increasing the convergence ratio, the yield of your deuterium-neutron yield is actually starting to fall off quite significantly. And that's quite interesting that actually you got, with these convergence ratios below 16, you can actually reproduce your neutron yield using radiation hydrodynamic simulations, which is a really fantastic result, because that means you can actually then start to plan and design your implosion facilities. So my student and I, Robert, were working on this kind of concept as well at the time. And essentially what we suggested was that we keep the convergence ratio below that threshold of 16. We have a maximum implosion velocity to 400 kilometers per second, in-flight aspect ratio of 1/3 compression. It's limited to about 30, and then we don't exceed the parametric instability threshold, which is 10 to the 14 watts per square centimeters per micron squared. In other words, when those four constraints are actually imposed, what happens? And this is a gain versus, this is the gain here against the drive energy, which you can see on this bottom axis. And you can see that to get a gain which is relevant for fusion energy, you can see that you need quite a lot of laser energy if you're just going to be sticking to the third harmonic. However, if you use the argon fluoride approximation, which is the 193 nanometer radiation, this is the blue curve which you see here, and you can get gains something like 20 with 2 megajoules of laser energy on target. And you actually start to exceed the threshold for ignition at around 1 megajoule. So that's rather nice, and we did the two color, so we can do the majority of the heavy lifting of the implosion using a third harmonic laser, and then right towards the end impose the argon fluoride laser pulse, and you see we got some really nice results there as well, which are really quite splendid. So one of my students, Jordan Lee, is now working on this topic. Robert graduated from his PhD about 2 years ago, is now working full-time at the Rutherford Apton Laboratory, and we're looking now at optimization of these implosions using this Bayesian optimization and particle swarm optimization methods as kind of a way of actually achieving significant improvements over those previous optimization attempts. So that's Jordan. He's actually upstairs at the moment, which is rather splendid. So at the moment, we were assuming in those calculations that the equation of state of the foam properties was the same as the plastic ablator, but with reduced density. But that was an assumption which we didn't know whether it's correct or not. So we had to do some experiments to actually see if this is correct or not. So I was leading a European research and development European grant called Routes to High Gain Inertial Fusion Energy, and it was an enabling research grant. It had 15 laboratories in 9 nations across Europe, and we did this experiment in early 2022, which was delayed due to the pandemic, of course. So here you can see the different laboratories involved in that. This was basically a method to interrogate the shock as it's propagating through the glass medium, and we're measuring the breakout and the rear surface temperature using a street optical perimetry diagnostic. And we found that there was good agreement with a wide range of 1D and 2D radiation hydrodynamic simulations using this uniform density equation of state models. So that's rather splendid. So here you can see the previous experiments being done at Los Alamos, at the École Polytechnique, at the Vulcan facility as well, and all of them are on this really nice Hugonio curve. So we've been continuing this not only with plastic targets, but also with glass aerogel targets, and we did an experiment at the Institute of Laser Engineering, where I did my postdoc. This is in Osaka University. So I did my postdoc in 1988 at the Osaka University, and the Gecko 12 laser facility, and we went back there to do this equation of state measurement, which is now under peer review with Physical Review E, and should be published in the next couple of months. You see Jordan has got this bear on it here, and in the Sackler, which is the X-ray free electron laser facility in Hyogo Prefecture in Japan. And this is the Norreys bear. So all of our students, if they go to an experiment either overseas or at a conference, they've got to take a photograph of the bear and bring it back just to show that they've been there and have enjoyed themselves. So we did another experiment in France, following on from that experiment. So this is Julian Matty as an undergraduate student at University College. This is Robert Paddock, Matthew Oliver, former student, but now a former student at Lady Margaret Hall. Gianluca Gregori's a student, and now he's a staff member at the Central Laser Facility. There's Bruno, Tommaso, and Stavros. And Stavros is here preparing the target, which you see here is a wetted foam implosion. And this one is what happens after you've hit it with our laser pulse. And you can see a nice explosion has actually happened, which is rather excellent. So that just goes to show we have some fun in this field. So Heath Martin, he's been looking at what's known as electrothermal instability. So imagine you have this hotspot being formed, and then the hot electrons are streaming out into the surrounding cold shell, and then you have a perturbation of the temperature along the inner surface. If you do that, then you have the higher temperatures have larger currents associated with them. With larger current, you have larger ohmic heating, and then essentially that perturbation then starts to grow. And then, so this is essentially here, we've got the hot spot with the hot electrons, and then the return current, maintain charge neutrality, and then this is the electric field which is set up to maintain that charge neutrality. Essentially, that means that you've started to build up a magnetic field, and which is rather interesting, because obviously we want to get gains of 30 to 40, maybe even 50 with these inertial bond fusion targets. If there is an intrinsic growth of the magnetic field that prevents you from depositing the energy in the surrounding field, then that's something we ought to know about. And as a result, that was published in Physical Review last year. As a part of his PhD thesis, he's now writing a Vlasov-Fokker-Planck code to actually calculate the electron kinetics and the ion and the alpha particle kinetics over the full duration of the burn. And it's computationally challenging, but he's completing this solver now with the great help of Linghao Yang over a couple of summers of his research program. So that's coming to a conclusion, and hopefully we'll be getting that in the press in the near future. And this is Roscoe Roskov. He's been looking at whether the effect of instead of having a monochromatic laser beam hitting the surface of the target, you have a laser beam which is broadband. It's the same intensity, but if it's broadband, it means that those you can basically break up the laser pulse into a number of beamlets, and then you can just say, well, obviously the growth rate is actually going to be quite significantly smaller in those beamlets. So then that basically reduces the plasmon decay instability driven by the broadband laser fields. So the knowledge of the growth is critical for estimating the levels of the nonlinear regime, and this is something that he has published in Journal of Plasma Physics last year. He's been working on the effect of turbulence on the plasma wave generation and on the growth and the saturation of the instability, which is part of his PhD. He's got some really brilliant results which he can tell you about himself in the near future. So that's it. I want to thank Jordan Lee, Ademir Elisev, Robert Mason-Sauker, Robert Paddock, Tom Jeffrey, Tony Arbour at the University of Warwick. And here's my group: Remy, Robin, Edward, Elliot, Abigail, Jordan, Heath, Roscoe, Robin, and summer students, Julian and Linghao. Again, thank you for that. And I've had master students this year, Ivo, Chen, and Xuanzhu, and all the students and staff in the Atomic and Laser Physics at the University of Oxford, all the staff at the Central Laser Facility, the Orion Laser Facility, and we've got collaborators in the United States at Lawrence Livermore, Los Alamos, and Laboratory for Laser Energetics. And of course, we've got collaborators in Eurofusion, European Union, Japan, and China. So it's quite a long list, but I want to thank absolutely every one of them for helping to contribute to our work. So thank you very much.
Thank you very much, Professor Norreys, for your talk. If anyone has any questions, we have around 30 minutes to answer questions, so please raise your hand. Yeah.
So you mentioned one of the experiments which involve generating or creating gravitational waves using lasers, if I remember right.
Yeah.
Could you tell us more about that?
Yeah. The idea of this idea came about because we're thinking that when you got to this burning plasma regime, you've got this 2 megajoules of laser energy, which is obviously going to be used for that purpose primarily. But can you do other experiments and fundamental physics experiments with it? And what we found is that let me just find if I can find a little example. So what we've got here is two neutron stars, as you know, twirling around, or rotating around each other halfway across the universe. As soon as they collide and merge, they generate these huge gravity waves. And then our detectors in the LIGO and nanograv and all these others can measure them. But if you have a laser pulse coming in with what's known as a Bessel beam, which is essentially structured so that you have a laser beam which is hollow in the center, but the electric field is spiraling around each other, then you've got kind of getting something which is kind of similar. But here you can put your detector about 2 millimeters away instead of halfway across the universe. So that actually allows you then to think about actually how you generate gravity waves using high power lasers. We've not got to the final conclusions yet, but it's an interesting effect and possibility for another use for these high power lasers. It's kind of fun. You see the electric field of the laser pulses spiraling around each other, similarly as you would with the gravity wave, the neutron stars rotating around each other. Normally, with electromagnetic radiation, of course, if it's just a plain wave, it doesn't generate any gravity waves. So essentially what you've got to have is a collision of two laser pulses, either head-on or, in our case, which is actually when you have a Bessel beam, we sort of essentially have a curvature of the curvature of the mirror, producing gravity waves, light waves, which are kind of plane but intersecting each other. So that actually then allows you to generate these gravity waves in the laboratory. Of course, it's quite a weak effect, and because it's still a gravity wave, you have to be clever about how you're measuring it.
So what energy scales does the lasers have to have in order to generate a detectable gravitational wave?
Well, that's interesting, isn't it? That's on my next slide, actually. Anticipated your question. So this is the National Ignition Facility. This is the distance of your detector. This is the log strain. And the ALPS detector is a 10 to the minus 37, so we believe that it should be possible to measure something along those lines. And with the National Ignition Facility, where is it here? This one here. It's really, really quite close to the source. But if you're out here, then you should be able to see 10 to the minus 37 is where you would expect to see with the ALPS 2 machine. So we should be able to see it if we are clever enough. So the National Ignition Facility you'd have to use a beam combiner to make every single one of those 192 beams into a single beam, and then you'd use a Raman amplifier to extract the energy into a short pulse. And if you do that, you can then get up to these types of strain rates. But it requires, we've combined up to about 20 beams on the National Ignition Facility. We've not combined all of them, so that would be a research problem in its own right. And the Raman amplifier is also another technology which is still to be developed. So it's kind of interesting, isn't it? If you want to do a PhD on this topic, then I'm always open to applications. I think the first week of January is the next application deadline. want to talk about inertial fusion? Have any questions on that? Please.
I have a question about, I think it was one of your students you said that was using Bayesian optimization.
Yeah.
I want to ask about the method for reducing the diagram that you had. Was it essentially like with each data point, a line then gets fixed at that point, and then there's gray regions, which I assume represent uncertainty.
Is the one?
Yeah.
Yeah.
So I should ask
Yeah, the idea.
that line is the mean of the predictions of like the sets of models that the optimization. But what does the
Yeah, essentially what you've got here is a wide range of possibilities for the Bayesian optimizer, and then it basically starts to optimize on these points here, and then reduces the variance around the curve, as you see here. So that's essentially what it does.
represent like, I'm assuming it represents like the classes of possible functions that like it could be. Like it represents the like if you drew any line that connected those points and went through the gray, it would be like reasonable. But how did you or he decide what the boundaries of the gray are?
Oh yeah, sure, I understand. Yeah. I think it's kind of these convergence ratio of direct drive wet foam implosions. So we basically did about 20,000 simulations, 11,500, sorry, with these direct drive configurations. So we basically had 7 different diameters of the shell. We imposed these constraints for the 4 parameters: the convergence ratio, the implosion velocity, in-flight aspect ratio. That's a measure of the initial shell of radius of the shell compared with the implosion at 1/3 compression. So that's the in-flight aspect ratio, and then the peak laser power. So we limited those, and of course we benchmarked the radiation hydrodynamics simulations which we were using against experimental measurements at the University of Rochester's Laboratory for Laser Energetics. And we also made sure that we were also benchmarking it against the National Ignition Facility, so we could get the absorption fraction close to what experiments have actually been observing at the LLE and also at the National Ignition Facility as well. Does that make sense? Yeah. Go on.
How do you initially create that kind of ball of plasma? Because doesn't it just want to sort of move out the way of the laser that we're trying to confine it or something?
Well, that's the whole idea, really, is that so essentially, if you illuminate this sphere uniformly, then there's nowhere for the plasma to go except inwards. So you've basically got to ensure that you have a highly uniform, either X-ray drive or direct drive illumination on the capsule surface. And of course, if you don't have that, then the pressure will go. You know, as you quite rightly said, I was always thinking of when you're trying to compress a balloon when you're having fun at Christmas time, you won't ever be able to do it because it'll just squirt out in the same way as you would if you're trying to do a curve compression. Yeah.
Which method of fusion do you think is more likely to be commercialized first, between the electromagnetic and and this one?
Yeah, that's a good question. at the moment, there are so many unknowns in terms of. Well, we've obviously, with the target physics, we've demonstrated more energy out than we put in, which is a good thing, and Lawson criteria has been exceeded. But there are many, many obstacles on the way to doing that. First of all, you can imagine that this experiments have been done 1 shot per hour at the National Ignition Facility. You've got to do it 10 times a second. So you've got to have the laser delivered 10 times a second onto the capsule. So that's going to be a laser technology development issue. Then you think about the radiation environment, which is the fact that most of the energy coming out is given by the 14.1 MeV neutrons, which are generated. And of course, some of them are going to activate the materials that are surrounding the vacuum vessel. So once you've actually got the fusion reactor going, you'll never be able to go into the fusion reactor directly. It's always got to be robotically controlled, and so on. And as I said at the beginning, it's so difficult to get these fusion reactions going that if you actually have any small misalignment of the targets or whatever, it's not going to it's basically not going to ignite for that particular shot. And then you've got to think about how you're going to do adaptive controls so that you're firing the laser beam so that it doesn't go down the other laser chain and destroy the machine. So these are big issues which we've actually got to try and find out real solutions for. So big challenges. It's not going to be really available, I don't think, until the middle of the century. But by then you'll be in your prime for your professorships. So you should be able to lead those campaigns.
Do you need a specific architecture for the fusion reactor to use this method as opposed to the magnetic one?
Sorry?
Like to use this as opposed to magnetic confinement, do you need a specific architecture for the fusion reactor, like a token specific?
The difference between the magnetic confinement fusion and inertial confinement fusion is that inertial confinement fusion, the target chamber, the driver, the tritium recovery, the heat, the thing you're going to drive the steam turbines with for the electricity generation, all of them can be decoupled one from the other. So we're doing the physics of the implosion at the moment, the target physics, but the others can be decoupled and run in parallel. With the magnetic confinement fusion device, it's exactly the opposite. You've got to integrate the whole thing and then see if it works. And if it doesn't work, well, you've wasted £1 billion or whatever the cost of these devices is. It's a pretty enormous undertaking. So I think in terms of the technology development, there's a great advantages to inertial fusion approach. But it's not to say that our magnetic confinement friends are wasting their time, because we can always learn from them. They're doing all the robotics and the remote handling and the tritium recovery and all these sorts of things which are required for both inertial and magnetic confinement fusion approaches. I think what's going to happen is we're going to learn from our magnetic confinement friends and then power on. Yeah, please.
Who funds the research for gas fusion in general?
Who funds the research? Well, the United States National Nuclear Security Administration has funded the work at the Lawrence Livermore National Lab. In the UK, we're funded by STFC and partially by AWE as well, Aldermaston. And EPSRC, of course.
Boiling water always really the best way to convert energy into electricity?
Sorry?
Boiling like steam.
It's rather 19th century, isn't it?
It always seems at the end of all of these reactors and stuff, is just boiling water and turning the turbine.
Yeah, I know. It's like the steam engine again, but it's a different way of doing it.
What sort of fields would you use for magnetic confinement?
Can you say that again?
What strengths of fields, how many Teslas would roughly be needed for magnetic confinement?
Oh, I see. About, I believe it's about 10 Tesla.
Is that the minimum?
Yeah. I mean, there are people in Tokamak Energy who are building superconducting magnets in order to get those field strengths higher.
I'm not sure it's ready, but do you have a plot that shows progress, like the rate of progress, and various parameters?
Yes, I think I did, didn't I? Where is it? Excuse me for a moment. That's the one.
Like over years.
So these are over 60 years, so there's a huge number of different experiments which have been done, funded by the national governments. So these are the Stellarator, Tokamak, reverse field pinch. This is a Z pinch. This is a MagLife, which is embeddedly confined inertial fusion, and so on. So this is a very large number of them.
Because if you were plotting it over time, it wouldn't be like, I guess I don't think there's any, but you have plot over time? Or
Well, these are the Omega laser facility was built in, came online in 1990, in the mid-1990s with its current configuration, with a 60-beam compression facility. So this is about 30 years of research effort. And National Ignition Facility is also came online in 2008 and just finished its, well, it hasn't finished yet, but they've achieved ignition in 2022. So that was 14 years of experimental effort, even before they actually built, obviously had to commission the machine and so on before that. So it was a huge effort by a vast number of people and some brilliant engineers and scientists and technicians. It's a big collaboration and a big effort.
Yes, to see the projection in the future and understanding, and for a plot that would help.
Well, the Americans are being very, they're being very ambitious, I should say. I think Joe Biden said that he wanted to have a fusion reactor on the grid in 10 years. And I think this is the latest roadmap, Fusion Science and Technology roadmap by the US Department of Energy Office of Science. You can actually go online and download it. It's about a 50-page this document. So it'll give you there what the American government are actually thinking about developing this thing. Okay. I would say if you're talking about the timescales, I would say that inertial fusion would probably be coming online towards the 2050s. So about 25 years' time.
Are there any other methods for confining the plasma? That like a mix of these or something else?
There is, of course, the wire array Z-pinch, which produces an X-ray drive, and then they use that as an alternative to the laser driver on the inner part of the hull ram. So that's a compression it's kind of a X-ray drive for using a wire-array Z-pinch. Maglev, I think, is a combination of magnetically confined fusion and inertially confined fusion, so there's a topic there. I don't know the details too greatly, but I can direct you towards those experiments.
Are there any further questions? Thank you very much, Professor Norreys, for your talk and for answering all our questions. Thank you everyone for attending.